Most of the time, when we're dealing with different analytical methods, such as regression, logistic regression, particularly, you're going to be dealing with different categorical variables as identifiers. And usually these values can have numerical values as, say, 0, 1, um, cancer, not cancer, whatever it may be. But a lot of times, using different methods, different models are going to require those category have multiple category variables. So oftentimes you can have more than two possible categories, three on up. And we can define those categories as flag variables or k minus one dummy variable is what it's sometimes called. And so if I take the instance, if I have a category of predictor variable for called region, for instance, that's four possible categories: north, east, south, west, right? I can define those as k minus 1. So I need to define three flag variables, for instance. Um, so I can define the north flag, the east flag, and the south flag. All right. And then I don't need to define the west flag since that region is already, as west, is uniquely identifiable by 0 because you've already identified or already defined what the other three existing flag variables are. So that's all this is really talking about, is how you can define dummy variables or flag variables that are more than just two variables that have two possible categories. Um, in other instances, we may need to transform our categorical variables into numerical variables. And so, in most instances, this may not be necessary. All right, and sometimes you may want to avoid doing it. The exception to this being a category variable that actually clearly has some order to it. So ordered categorical variables are a thing. All right, and so you can do this by assigning numbers to them, and so that if they have a specific order to them, you may want to assign values to them. In this text, we use always, usual, sometimes, and never as an example. Another example may be like high school. So freshman, sophomore, junior, senior obviously has a progression to it and therefore is a order to it. So you might assign freshman as the value of 1. All right, sophomore is the value of 2. Junior is the value of 3. Senior is the value of 4. So there is a progression to those categorical variables that are clearly ordered. And so oftentimes that's easy to do by assigning numerical variables to them if they're ordered in that way. Binning numerical variables is another way to create predictor values based on a continuous numerical variable. And so sometimes we want to create a categorical variable based on numerical values. And so there are ways to do that. And one way is by binning. And so we can bin these numerical variables. And the four common ways for binning are equal width, equal frequency, binning by clustering, and then binning based on a predictive value. All right, equal binning is when we partition X into the following categories of equal width. All right, and so if I have, say, a value, I think in the next slide we have a illustration of this. So if I have values going from 0 to, say, 45, all right, I'll split up the first categories between 0 and 15. All right, 15 to 30, and then 30 to 45, right? I think that's how it is, yeah. And so then we'll have low, medium, high based on the equal width of each one of those particular categories. The problem with this is that, especially in this data set, we end up with data values mostly being in the lows, all right, nothing in the middle, and then 1 in the high. So we don't really get an equal distribution of all our values in each one of our categories, which is oftentimes what you want to do when you're trying to bin these numerical values. Equal frequency binning. Say we have the number of observations is 12. We want to split this into 3 different categories. So we take n minus 12. So there should be 4 different distributions or 4 different categories. Is that right? Nah, it should be 3. Sorry. there should be 4 numbers in each of our categories. Sorry about that. Low, all right, ends up only containing x equal to 1. Medium, all of our 4 data values here. All right, and then high contains the last 4. So we do a little bit better job with the equal frequency, but we get some overlap with our distribution as well. K-means clustering is another way of doing this. We're going to talk more about the K-means algorithm later on, all right, for clustering, but is based on the ability to be able to cluster these based on certain tendencies or based on certain attributes within the data set itself. And so we'll talk about that later on. All of this is done is reclassifying these categorical variables. That's the equivalent of binning the numerical variables. So oftentimes the categorical variable will contain too many fields. And so what we want to do is reduce the number of categories in that variable based on some relationship that they have between the variables. And so we'll talk a lot about this logistic regression, decision trees. If you have too many fields or too many possible categories, they don't do very well with that. And so what we can do is re-bin or recategorize these categorical variables to make them a little bit more, and usually based on some kind of similarities in these categorical variables. For instance, if we have 50 states, you don't want to have 50 different classifications or 50 different categorical variables, right? And so at least maybe you don't, right? And so we can split these up into region and redefine what the categories are. And so we can have a northeast, a southeast, a north central, whatever that is, and put those states into those easily binnable categories. Removing variables that are not useful. All right, you may want to remove variables that are not very good for your analysis. These are variables that are not going to help you in your data mining task. And some of the examples here are urinary variables. These are values that only have one single variable or one single value. And so there's not very much good variability within that particular variable. And so it acts more like a constant. And a lot of the times when we're doing statistical analysis, we don't necessarily need an entire variable to be a constant, right? We need some variability in there to draw any inferences out of it. Sometimes the variables can be nearly urinary, all right? So suppose that you have 99.95% of the players on a data set, field hockey league, are female, and the 0.05 are male, all right? That's nearly a constant, all right? And so sometimes that may not be necessary or may not draw much inferences. It could, maybe, I don't know, if we were trying to draw inferences on male field hockey players on a female team or something, I don't know. But maybe that wouldn't, be useful for looking for trends in a urinary data set. So it is common, all right, though questionable, to remove different variables from the data set, all right. Oftentimes, if you're missing a lot of data in a data set, so variables that are missing 90% or more values, you may think about removing, all right. Because if you have over 90% of your data in a value or in a variable is missing, that's going to present a challenge, all right? You can do that through mutations of that data set and handling that missing, either through one of the means that we talked about or some other means. But it is oftentimes, often you want to look at why you had that much missing data, all right? Such as if you have a data set where you're dealing with donations, maybe those a lot of people are inclined to skip that survey question about donations and don't want to talk about it, all right? And so maybe that's good information or something that could be challenging, but you could talk about in the data set. Another one is correlated variables. You may not want to necessarily remove those correlated variables, however closely correlated they are to one another. Oftentimes, we can instead use principle like PCA, principal component analysis, to draw out correlations by transforming that data set into uncorrelated principal components and then talking about what those principal components are. Duplicate records are challenging as well. This can lead to overweighting of the data values in those records. So if we have a lot of duplicate records, that can be problematic. And so oftentimes we need to deal with that in particular ways. Do you want to remove duplicates from your data set or keep them? Or do you want to keep one unique value or one unique observation of the data set to help draw out more inferences as well? And then finally, a little bit about ID fields. These are oftentimes not beneficial or helpful in any kind of downstream data mining algorithms. So oftentimes we remove these from our analysis. And so oftentimes you're going to see just these come out of databases. We've talked a lot about ID fields when we talked about databases. And so oftentimes when you glean or grab information from a database, you're going to have all of these observations that are automatically labeled based on their numerical place, right? So 001, 002, 003, so on. And so it's recommended that those ID fields should be filtered out and removed for your data analysis. It's not going to be any helpful or do anything to help differentiate between similar records. All right. So that's it for this discussion. If you have any questions, feel free to email me, and I will talk to you guys later. Have a great day.